Welcome back. This PowerPoint is looking at forces and how to do free body diagrams. It's really not that difficult, just don't overthink it, okay? It actually is really simple. By the way, to actually do these and hand them in, I either recommend do them on a drawing program like MS Paint, or you can just use boxes and arrows on Word and then hand in the Word file. So, what is a force? A force is basically any push or pull that an object has. It can be due to anything, mechanical, electrical, magnetic, whatever, but basically it all just comes down to how hard are you pushing or pulling on it. So it is a vector quantity because it really matters what direction you're pushing or pulling something as to what it actually does. So it has a magnitude, that's how hard you're pushing, and a direction, which is what direction are you putting it in. So it can be represented with a vector diagram. The symbol for force is a capital F, and the unit is called the Newton. And a Newton is how much force it takes to give a 1 kilogram object an acceleration of 1 meter per second squared. So, there are 4 types of forces: gravitational, electromagnetic, strong, and weak. All of those basically contribute to the forces that we see when we actually push or pull something. The gravitational force on an object, or F little g, is the pull of Earth on an object. It's always down. So an object sitting on a hard surface, the reason it doesn't fall through the ground is you always have a force equal to the force of gravity, but up. And we call that the normal force, or Fn. So if you can see in the diagram, you have the force of gravity down, the normal force is up, they balance each other out, which is why you're not falling through the ground right now. The forces we're going to deal with in this course are called mechanical forces. So they're caused by some physical push or pull, not some sort of other weird thing like, magnetism or electricity. It's actually physically pushing something. So the force you apply to something we tend to call the applied force. So F with a little a after it. The force of friction is the opposition to motion. Every time something's moving, friction is trying to stop it. Tension would be the force on a rope or spring. And air resistance, we're just going to ignore because you can't actually do anything with it if you don't know calculus. And not the easy calculus either. So, how we show forces on an object visually is called a free body diagram. Now the main thing with this is don't overthink these. You draw the object usually as a square, and you draw arrows from the object in the direction the force is acting. And just make the length of the arrow about the same as the magnitude of the force. So in this one, if the applied force was twice the force of friction, you draw it twice as long. As I said, the big thing with this is don't overthink these. These shouldn't take more than a few seconds to make. So, the rules. The first thing we're going to do is you need to draw a frame of reference and a scale. So basically, usually, we might just say, this direction is north, that direction is south. Or I might say, this is up, this is forward, this is backwards. Just so that I know what you're describing. Then, you draw the object. Really, it only needs to be a square. It doesn't even need to be that neat. Then you draw all the forces on the object as arrows from its surroundings. So let's say there's gravity pulling down. A normal force is keeping it from going, from falling. And maybe we're pushing it forward, you'd have a force forward. And if there's a force of friction slowing it down, you'd draw that at the back, and then you'd label them. Okay, really, that's all it is. The only important thing is you only draw forces acting on the object. Okay? You don't draw forces done by the object, because you're going to see those don't actually even affect what the object's doing. So, for example, a free body diagram for a student holding a backpack. Well, force of gravity is pulling it down, strap's pulling it up. The backpack's not falling, the kid isn't falling over, so they must be balanced. So you draw them equal. Car hitting the brakes. Force of gravity down, normal force up, force of friction backwards. Again, not really an issue. Actually, by the way, the main mistake people make on this is they draw an applied force forward, which doesn't really make sense unless you're an old person who keeps your foot on the gas while you're hitting the brakes, right? If you're not applying the gas, there's no force forward. That's why your car stops, right? So the main thing with free body diagrams is don't overthink them. They're not really that hard.